Okay, so we're just picking this up right where the last video left off. And remember what we had done is marked where h and k are at +2, -2 on our graph. And now we're going to go back and do next what they suggested we do first. So this is actually our number two step. We're going to take the rest of our equation that's not hk, the beginning part, and we're going to put in 0 for x first. So y equals 2 times 3 to the 0 power. And remember, we don't need h and k. They're already marked on the graph at our point. So 3 to the 0 power is 1. So 2 times 1 is 2. So we put 0 in for x, and our output is 2. So our point is 0, 2. But I'm going to graph that beginning at my hk point, this red point right here. So I'm going to go 0 left to right and up 2. Okay, remembering that this point down here, our hk point, is kind of like our origin for this problem. Okay, so now we're going to put in +1 for x. So I'll do that over here on the right. We're going to have y equals 2 times 3 to the first power. Again, we're not going to use the h and k values. They've already been accommodated for. That's a very sloppy equal sign. So I have 2 times 3, which is 6. So my next point, when x is 1, y is 6. So I start again at my hk point down here at 2, -2. From there, I go to the right 1 and up 6. Okay, the next thing I'm going to do is draw my asymptote. I want to make sure that I have that drawn before I try to draw my actual graph. So I want you to think about this. On our parent function graph, we had an asymptote at the horizontal axis, at the x-axis. But when we marked h and k, we said, hey, this graph has been shifted left and right, and it's also been shifted down. So having been shifted down, I should be able to grab this. There we go. Our asymptote gets shifted down right along with that new origin. So that means our asymptote is at point, or at the line, is the line y equals -2. So if you're paying attention to this, the k value will always be the equation of the asymptote. So I'm going to say that again. Your k value, because that shifts the graph up and down, will always be the value of your asymptote line. And you always want to draw that asymptote with a dashed line. Okay, now I'm ready to actually draw my graph. So I'm going to start over here close to the x-axis. I'm going to make this as smooth of a curve as I can, and then just continue my curve up. Put arrows at both ends because this graph is going to go on, and that's a not too bad graph, okay? Fairly smooth. The domain here is left forever and right forever. You can see this graph is heading up pretty steeply because we have this a value of 2 and this b value of 3. So those are pretty big. It makes the graph go up pretty fast, but it's never vertical because it is a function. So the domain is all real numbers. It's going left forever and right forever. The range, remember, our asymptote is like our wall. It can't go below that. So y is greater than -2. Or if you prefer, you can write it -2 is less than y, which is less than 0. Less than or equal, to infinity. Less than or equal to infinity. Either one of those notations is fine with me. Okay, so that is our graphing. Down here below, there's a checkpoint for you to practice on your own. So I'm going to ask you to pause the video, graph this on your own, and then turn the video back on, and you can check it against my work. Okay, so with an HK value of -1, -3, we've gone left 1, down 3, and started there as our origin for this one. I drew my asymptote through that point, and the equation of the asymptote is y equals -3. That's one of those things we want to write. My points I found by putting 0 in for x first, and I got 0.01, which I plotted down here in green. Actually, I plotted it in blue. I'm sorry, you just kind of covered up. And then my next point, I put in 1 for x, and I got 0.18, which is actually on the y-axis up here at +6. And then I get a very steep exponential growth graph here because that A and B values are big enough. It just makes the exponential growth go really fast. So there you go. We should write domain and range. The domain here is all real numbers again. It is going left and right forever. And the range, we could put y is greater than -3. Or if you want the other way, -3 is less than y, which is less than or equal to infinity. There's an equal there. I can't get it to write the equal sign because these dots are in the way. I don't know. Okay, sorry. There is an equal sign there under the equal, under the less than or equal. Okay, onward. So now we're going to look at where do these exponential growth functions come? Because they are all around us. We see exponential growth in a lot of things. Population grows exponentially. People, animals, all those things, the population increases at an exponential rate. And in today's world, a lot of things are increasing exponentially. Things like the amount of data is increasing exponentially. How much we use technology is increasing exponentially. The availability of technology is increasing exponentially. So there's a lot of things in our world that we see exponential growth. But right here, we're just talking about population of buffaloes. So it says here that in the last 12 years, an initial population, so that would be 12 years ago, they started with 38 buffaloes in the state park. And then the growth rate was 7% per year. These are the important values we need. So we're going to write an exponential growth model, and we're going to remember that we start with this. Y equals a b to the x power. Okay, so we always start with that. So the initial amount is our a value. A is always the starting amount. And in this case, the starting amount was 38. So we're going to fill that in down here at A. A equals 38. The percent of increase is 7%. Now, in this case, what we do, and they've kind of written it down here below, so our rate is 7%. We're going to write it as a decimal. So 7% written as a decimal is 0.07. Percent is per 100, so 7/100 is 0.07. So we're going to write that in here for R. So when we actually write this equation, we had this y equals ab to the x. Well, b is going to become, for exponential growth, 1 plus r. 1 being the fact that when we have growth, we keep all of what we had. And then we add on this extra percentage. So 1 plus r means we have our initial amount, a, times all of a plus a percentage more of a, and then it's over time. So the exponent we often use instead of x for exponentials is t. We often use t. It means the same thing. Okay, it's just our exponent. So we're going to fill in our numbers now. N is going to be the number of buffaloes, so we'll leave that as n, equals a, which is 38, our initial number of buffaloes, times 1, all the buffaloes, plus a percentage more, 0.07, to the t power. And so you notice we're using n for number of buffaloes instead of our usual y. We're using t as a substitute for x because this is over time. So when we simplify, we're going to add together the 1 plus 0.07 to get 1.07 to the t power. Okay, so we can use that equation now to determine or to figure out how many buffaloes there were at any particular time of this problem. So they go on to say, using this model, we can estimate the number of buffalo after 7 years. Some of you might have been thinking, hey, it said something about 12 years in the problem. Why didn't we put 12 in for t? Well, we'd only put 12 in for t if we wanted to know how many buffaloes were there at the end after 12 years. But we can use this model for time in between. So to do that, we would put n equals 38 times 1.07 to the 7th power. And then you can just put that in your calculator. So we have 38, and put that in parentheses, then 1.07, and then caret, and to the 7th power. It should look like this, and enter, and we get, and you notice it's a decimal, so we're going to round this off. This is buffaloes, so I'm going to round it off to the nearest buffalo. It's about 61 buffalo. So after 7 years, they'd gone from 38 to 61 buffalo. Now we can also graph this. The graph passes through the points. We're going to use our 0 and 1. So n equals 38 times 1.07 to the 0 power. Means we have 38 times 1, because anything to the 0 power equals 1. So when our t was 0, x was 38. And so what we're going to do, you'll notice there's no h and k here, so this graph has not been shifted up or shifted down. So we're using the x-axis as our asymptote. We can mark that along there. And so we mark 0.38 on our y-axis because there's been no shift away from the origin. Okay, so now we can put in 1 into our equation. N equals 38 times 1.07 to the 1st power. And this I'm going to want to put in my calculator because I need 38 times 1.07. So I'll do that. 38 times 1.07. And I don't need to worry about that 1st power because 1.07 to the 1st power is 1. And I get 40.66. So I'm going to come over here to my graph, and I'm going to go right 1 and up to approximately, it's just a little bit more than 40. Well, that doesn't give me a whole lot of information. I might like to get one more point, but I actually already have one. Because up here we found that when t is 7, so when t is 7, the number of buffaloes was 61. So I can mark that one. At 7 years, I've got 61 buffaloes. So that gives me a little bit better idea of this graph. I can't worry about going all the way over to the left. I'm just going to start because these are buffalo and we don't have negative years. So we're just going to start here and gradually head up. That's not very neat. I'm sorry. This is almost, this is such a gradual increase here that it's just not going up very fast. It's going up very slow. I need to draw this a little better. So maybe you do too. So we just are going to go up gradually, and it's going to continue up gradually. It's going to go very slow. So that's the answer to this, and we can see that we could estimate the number of buffaloes after 53 years if we were to continue this graph, or 53 buffaloes. 53 buffaloes was right in here somewhere. It's a little bit hard to tell on our inaccurate graph, but I'm going to say 53 must be in here. And they're saying about 5 years. So we're going to believe him. So that's the end of this